This is an abstract of my talk. My problem is to estimate parameter of the probabilistic model by solving optimization problem like this for discrete, and we consider a discrete probabilistic model such as Boltzmann machine or something like that. And the difficulty of this kind of problem is normalization constant. For example, a Boltzmann machine has a normalization constant written like this, and this is very hard to calculate. So my motivation is I never want to calculate this normalization constant. This is my motivation. And I propose some estimator to estimate parameter based on the homogeneous divergence and generalized empirical localization method. I mean, this homogeneous is, scale invariant divergence spoken in the talk of the Frank Nielsen. So, okay, this is a setting of the problem. X is some input in the in high-dimensional discrete space. For example, this is a binary d-dimensional vector, and P tilde is an empirical distribution of the data set. And this bracket of bracket f is the summation of the function f on the all domain X. And this Q theta is an unnormalized model. So this is not the probability function, so a summation of the Q is not equal to 1 in general. And the probabilistic model is written like this, Q bar theta. So this is normalized by the theta, so this is a normalization constant. And we never compute this normalization constant. So this is a simple example of the unnormalized model. For example, Bernoulli distribution, probabilistic model is written like this. So unnormalized model is this, and normalization constant is written like this. And the Boltzmann machine is written like this. So unnormalized model is written like this. Or another example is hidden restricted Boltzmann machine, but I omit this slide. Okay. So to estimate the parameter, very classical method is maximum likelihood estimator. So MLE is computes the estimator by maximizing this quantity or this quantity. Sorry. This quantity. But we cannot solve this optimization problem explicitly. So we usually use a gradient method, and the gradient is written like this. Actually, this first term is easy to calculate, but this second term is very difficult to compute because this term includes the normalization constant here. So many approximation methods has been proposed, such as near-field approximation or MCMC sampling or something like that. And in this talk, I consider a method based on the homogeneous divergence and empirical localization. In the following, I will introduce, I will briefly explain the homogeneous divergence and empirical localization and existing estimator based on these two methods, two concepts. And I propose a new estimator based on the generalized empirical localization. So, okay, first one is homogeneous divergence. This F and G is some positive measure, and gamma is a positive constant. Then homogeneous divergence is defined like this. This divergence is called gamma divergence. And this is always non-negative. And this is divergence is equal to 0 if and only if. f is proportional to the g. So this is a big difference from the Kähler divergence or Brekman divergence. And this homogeneous divergence converges to the Kähler divergence in the limit of the gamma to 0. So actually, this kind of simple combination of the homogeneous divergence and unnormalized model does not work. This is a simple note on the homogeneous divergence. So, for example, Q is an unnormalized model, and let us consider the homogeneous divergence between the empirical distribution and unnormalized model. Then this divergence is written like this. Actually, this second term is almost equal. I mean, this second term requires the same order of the computational cost for the normalization constant, because this is just a summation of the unnormalized model. So this does not work well. So I introduce a second component of the method, empirical localization. Actually, empirical localization of the unnormalized model Q by the empirical distribution P tilde is written, defined like this. Actually, defined like this. And this R tilde is a model on the E geodesic between the empirical distribution and unnormalized model Q. So R tilde 0 is equal to the probabilistic model Q bar, and R tilde 1 is equal to the empirical distribution. So this R tilde is connects the two distribution, empirical distribution and target probabilistic model like this. The alpha is some constant. Actually, how I explain how empirical localization works in this slide. Actually, this numerator, this one, is written like this in our problem setting. If x is observed in the data set, this term is equal to this, and otherwise, this term equals to 0, because empirical distribution is equal to 0. This nx is the number of the x is observed. So this bracket of this p tilde alpha q theta 1 minus alpha is also easily calculated like this. This summation is defined on the domain of the observed sample, so it is very easy to calculate. So why I call this empirical localization is explained in this. I mean, we can ignore unobserved domain by this equation, because if x is not observed, this is equal to 0. So this is localization. And this term is very easy to calculate. So this is a simple example of the empirical localization. So let us consider the two-dimensional binary space. So we have four candidates of the sample, and we have an empirical distribution like 3 over 5, 2 over 5, 0, 0. So this term can be calculated like this. So we can ignore the unobserved sample completely. So this is an existing estimator proposed by me and Kanamori. This is appeared in NIPS 2015. So this estimator is defined by the minimization of this score function. This score function is a homogeneous divergence between two kinds of empirical distribution model. And this score function is written like this. And why, I explain why this works. briefly. This score function is equal to 0 if and only if this two term, I mean this two kind of empirical distribution is proportional. And this equation is proposed equivalent to this. So if target model is proportional to the empirical distribution, this score function is equal to 0. And second important point is this term or this term or this term is very easy to calculate. We don't need to calculate the normalization constant. Actually, this is a geometrical picture of the estimator. This space is a probability space, and this is empirical distribution. This is a manifold of the probabilistic model. So usually, for example, a minimization of the Kähler divergence corresponds to the orthogonal projection of the this model to the this empirical distribution to this model. And in this estimator, we consider the two kind of empirical localization model between this P tilde and model Q, like this. And we minimize this pink quantity. So this is a very intuitive explanation of the estimator. So I introduce some statistical property of the estimator here. This estimator is Fisher consistent. So I mean, this is Q is a normalized model, and let theta 0 is the true parameter of the model. I mean, P is equal to Q bar theta 0. So arbitrary theta 0, true parameter satisfies the stationary condition like this. So this estimator is a Fisher consistent. And we can write down the asymptotic distribution of the estimator. So asymptotic distribution of the estimator is written like this. So I mean that this estimator has normally distributed around the true parameter theta 0, and the covariance matrix is the inverse of the Fisher information matrix. So this is one important remark. I think asymptotic efficiency of this estimator is equal to that of the MLE. So asymptotic efficiency does not depend on the choice of the alpha or alpha dash or gamma. So this is important point. And this is one characteristic of the risk function. Okay, this is estimating function of this risk function. So this is estimating function is written like this. So this is a difference between the expectation of the sufficient statistics with respect to the two kind of empirical localization model. On the other hand, estimating equation of the maximum likelihood estimator is written like this, or written like this. So by comparing these two kind of equation, in the limit of the alpha dash to 1 and alpha to 0, this estimator may behave as a maximum likelihood estimator. Okay, this is an existing method. So, and in this talk, I propose this estimator by extending the concept of the empirical localization. And I will investigate statistical property of the estimator. Okay, empirical localization is originally written like this, and this can be rewritten like this. or like this. This is completely equal. And we generalize this empirical localization like this. U is some positive monotonically increasing function, and xi is an inverse function of the U. So I replace exponential to U and logarithm to xi like this. So this is a generalized empirical localization. Actually, we can set xi1 to 0 by considering the variable transformation like this. So we can always and this generalized empirical localization is has a property like this. If we set alpha equal to 0, this is equal to the unnormalized model. And if alpha equal to 1, this is equal to the empirical distribution. And this generalized empirical localization model is written like this. If x is observed, or written like this, and otherwise, this is equal to 0. So we can also ignore the domain of the unobserved examples. So this is examples of the generalized empirical localization. So if we consider the function like this, xi is written like this, and empirical localization model is written like this. Or for the beta function, this generalized empirical localization is written like this. And estimator is just a combination of the generalized empirical localization and homogeneous divergence. So we consider the risk function by the homogeneous divergence between the two kinds of generalized empirical localization model like this. So question is, how does the function U affect the statistical property of the estimator? This is my question. And yeah, actually, this estimator has also has Fisher consistency. So true parameter is always solution of the optimization problem. And yeah, asymptotic distribution of the estimator is also normally distributed like this. And covariance matrix is inverse of the Fisher information matrix. So I mean, asymptotic efficiency of the estimator is also equal to that of the maximum likelihood estimator. And asymptotic efficiency does not depend on the choice of the alpha or alpha dash or gamma or function U. Okay, almost. This is a conclusion. We construct an estimator for discrete probabilistic model by combining homogeneous divergence and generalized empirical localization. And the proposed estimator does not require the calculation of the normalization constant, so it is very easy to construct. And generalization of the generalized empirical localization does not affect asymptotic efficiency of the estimator. Okay, so that's all. Thank you very much.